We have a couple of topics that I would like to treat with you, to discuss with you before Friday. And one is probability theory, and the second one is sustainability of water resources management, sustainable water resources management. So I think that sustainable water resources management will be dealt with on Friday. Tomorrow we will meet as usual in the other room on the other building, bring your PC, and we make tomorrow the final exercise, okay? So, talking about probability theory, we came here, as you may remember, because we highlighted that we need in several applications of sustainable design of water resources system to know the peak flow for a river. And therefore, we said that in order to estimate the peak flow, we have several alternatives, but for sure the most interesting one is to use probability theory. And so we started to discuss probability theory. And you may remember that I promised to be short and to be very technical and not much theoretical, and this is what I would like to do indeed. And at the end of this treatment, I will also mention some alternatives to the use of probability theory for estimating peak river flows. We are referring here to peak river flows, but please keep in mind that the same concepts, the same theory applies for the estimation of the probability and therefore frequency of occurrence, because we already mentioned that probability from a technical point of view means frequency of occurrence of any random event. And you may have to use probability theory for several designs, projects related to water resources systems. So we are referring here to peak river flow, but the same concepts apply, for instance, in coastal engineering for estimating wave heights and wave forcing. The same concepts apply for the estimation of demographic expansions and future water resources demands. So it's very general, okay? We stopped when we were defining what probability is, and we said that probability describes random events, and in order to describe them and to treat them mathematically, we define a random variable. A random variable is nothing else than a transformation between the space of the random events to the real number, the space of the real numbers. And therefore, for the river flow, we associate with the event that we observe the river discharge. And basically, probability, what does probability describe? The likelihood of an event. And in particular, we said its frequency of occurrence, because likelihood means frequency of occurrence. And probability, we already mentioned, that is defined through a number that is varying between 0 and 1. And I said, and I closed my last lecture by saying this, that there are several possible definitions of probability. First of all, let's provide a general definition of what probability is. And the first definition that I provide, as I said, is very general, and then two specific definitions. So the general definition is just the fact that probability is a number between 0 and 1, which meets the Kolmogorov axioms, and this is the Kolmogorov definition of probability. So what are the Kolmogorov axioms? They are very simple. So don't be concerned by the word axioms, because indeed axioms are just statements that we don't prove, we take for true, and in this case they are very simple. Let's see in particular these axioms, so we understand that indeed they are very simple. They are three, and here they are expressed in mathematical terms. I translate in technical terms. The first axiom says that probability is a real number that is greater than 0 for any event that we consider. E here is the event, and you can substitute here to the event the random variable. But in any case, what is important is that probability is greater than 0. And also, the second axiom says that the probability of an event that is certain is 1. And this is what we already introduced last time. The third axiom is probably the more complicated to understand, but it's not really complicated, because it says that if you have these joint events that are mutually exclusive, so you consider a phenomenon. And then within this phenomena, like tossing a coin, you have two events that are disjoint and mutually exclusive, like tossing a coin, you have head on tail. If you have an head, you don't have a tail at each experiment, so it means that they are exclusive. And completely disjoint means that there is no superimposition between them. You can't have a result that is mixed between head and tail. So, basically, coming back to the axiom says that if you have two events disjoint that are mutually exclusive, the probability of getting the union of the two events is equal to the sum of the probabilities of the individual events. So, what is the probability by tossing a coin to get an head unified with a tail? So, an head or a tail. It's the sum of the probability of getting an head plus the probability of getting a tail. So, the probability of getting head or tail, which means the union of the two, is 1. If you exclude, you give 0 to the probability that the coin remains standing on its side. You exclude it. Of course, the probability of getting an head or a tail, which means the union of the two, is 1. And it's equal to the sum of the probability of getting an head plus the probability of getting a tail. So these are the three axioms, which are very simple. And there are some consequences. The most relevant one is that probability is included between 0 and 1. And the first one, which maybe it's as well relevant, is that the probability of the impossible event is 0. And it is a consequence of the axioms. And therefore it follows that probability is between 0 and 1. Certainty means probability 1. Impossibility means probability 0. That's it. But this is a very general definition. And in particular, it doesn't say how you estimate probability. It clarifies what is probability. It's important, but it doesn't say how we estimate it. So, if we want to concentrate on how we estimate probability, we may provide two more specific definitions. And the first one is called the frequentist definition, and there are links in Wikipedia, but I prefer to explain because so I can use technical terms. The frequentist definition of probability is, as I said, a second definition, which is different with respect to Kolmogorov's definition, but we will see that they are compatible. So, what is the frequentist definition of probability? Let's refer to an event. So we want to estimate the probability of an event. So let's refer to the event now, not yet to the random variable. And let's assume that for this event we can perform experiments. For the case of tossing a coin, it's very simple to perform experiments, but even for the case of the peak river flow, because we may go on the river and observe whether the river had overtopped. So for instance, we may go to a river each year at the end of the year and get information on whether or not the river had overtopped. So we may see that in some years the river overtopped, in some other years the river did not. And let's assume that we perform either with the coin or with the observation of the river. Let's assume that we perform a series of n experiments. And let's count the number of times that the event occurred, the considered event occurred. So if the event is the outcome of an head from tossing a coin, let's count the number of heads. If the event is the river that overtopped, let's count the number of overtoppings. And let's call with this number with lowercase n of e, so the number of events. And this number of events, lowercase n of e, is of course less or equal than the number of experiments. Okay, so we may estimate the probability of the event E as the ratio lowercase n of E divided by n. This definition of probability, which is called again the frequentist definition, satisfies, it's easy to prove that it satisfies the Kolmogorov's axioms. It's easy to see that it's a number varying between 0 and 1. It's easy to see that if you have a certain event, the probability is 1. If you have an impossible event, the resulting probability is 0. And it's easy also to prove that if you have two disjoint outcomes, the probability of the union of the two outcomes is equal to the sum of the individual probabilities. But this is a definition that tells you some more because it gives to you an indication of how to estimate it. Actually, I was too fast, sorry for that. There is one more step that I need to make because I forgot to say that this definition is valid only if n is very large. I forgot to say this, so I need to correct now my mathematical formulation. Because you understand that if n is not large, this definition may be incorrect. Let's suppose that you toss the coin just once. Of course, you get an head and you get the probability of the head is 1, which is not correct. You have to toss the coin like Pearson thousands of times. I told you that Pearson tossed the coin 24,000 times in order to prove that probability was indeed, and in particular this way of estimating it was working. So in order to make this further step, let me make a small correction. What I estimated here is not the probability, because it would be the probability n was very large. What I estimated here is the frequency of occurrence of the event within my experiment. This is indeed the frequency of occurrence, and this is why this is called the frequentist definition of probability. So, how can we define the probability? It's, as I said, I need one more step. V of E is equal to the limit for n tending to infinity of Fe. That's it. Sorry, I needed to make this further step. I was too quick. But this is also nice because we have the opportunity to discuss what is frequency. So you can understand two things. First, why this is called the frequentist definition. Buongiorno. Sì, sa che stavo valutando che i ragazzi mi sembrano solo 9, 4, 5. Do you know if somebody else is coming? Because less than 10 is a bit problematic. Because it doesn't count for the statistics. Sorry? Yeah, correct. This is very true. Senta.
Se non preferisce che io passi.
Proviamo a fare una cosa magari, perché adesso a volte qualcuno arriva in ritardo, altrimenti però non so bene come fare perché finisco venerdì, domani pomeriggio dubito che... Allora facciamo una cosa, guardi, potrebbe per cortesia ripassare tra un'ora, che vediamo se...
Assolutamente, è perfetto per me.
No,
Perfetto. Grazie mille.
So meanwhile, if you have the opportunity of sending an email to somebody, because for the law of the large numbers we need at least 10, otherwise it doesn't count. And it is not considered by the uni, and I would prefer to avoid this outcome. And otherwise, if we are not at least 10, 11 within an hour, I postpone to tomorrow, I make this attempt. And okay. So, again, second consideration, you understand why we say that probability from a technical point of view, is the same thing as frequency. You perfectly understand from this definition. Okay, this is one definition of probability, but of course it may be used if you have the opportunity of performing an experiment, because otherwise you cannot use it. And in our case, performing the experiment usually means to have data. So we are talking about river flows. If we have historical data, we can perform experiments, which means look at the data. If we don't have data, we can't use this definition. And therefore, we need another way of computing probability. And the same applies, for instance, to elections. You cannot, as I already mentioned to you, you cannot perform several elections in order to estimate the probability of winning for a party or a candidate. You need something different. So, what is another possibility? Another possibility is to make a guess, of course. As I said last time, you look at the coin and you say, of course, the probability of getting an head is 0.5. Of course, this intuition, this guess, is not supported by an experiment. So maybe that the coin is not fair. Maybe that it's loaded. Loaded means that you have a higher probability of getting an head or a tail. And you may not understand it. But still, guessing, it's a very interesting opportunity. And guessing is not a good word, because guessing seems like we are just, you know, by chance, and without any physical consideration, we are trying to attribute probabilities. It's better to say that we assign probabilities based on our degree of belief, which is better than guessing. So, you basically analyze your degree of belief in the likelihood of an event, and you express the probability. So, let me then turn to the Bayesian definition. The Bayesian definition, indeed, of probability, which is something that may be a little bit scaring, because, you know, it's a name that is difficult to remember, and but it's nothing else than assigning probabilities based on the state of our knowledge, based on our degree of belief, or basing on partial information, incomplete information, or basing on proxies. Like for the elections, the pools. You make a pool, you interview a lot of people, and basing on their replies, you elaborate proxies. Of course, it's not like making the experiment. It's not like making the election. In fact, recently you may have heard that in several election pools they failed. The last one, the most famous one, was the presidential election in the US. They failed. And they failed after several other occasions in which they proved to be very successful. Because, you know, proxies are, sometimes they may be reliable, sometimes they may be not. But indeed, for the case of these election pools, people don't just use their degree of belief. They also get some additional information. And this is the way in which you assign the Bayesian probabilities. Of course, when you assign these probabilities, you have to make sure that you meet Kolmogorov axioms. Okay, there are some people who say this is not really necessary, because Kolmogorov axioms are nothing else than another definition of probability. But I would say that from a technical point of view, it's advisable to make sure that they are respected. And what does this mean? It means to make sure that you assign zero probability to an impossible event. Like for an election, if you have a third candidate that is not listed, and you know that the laws doesn't allow people to vote for a candidate that is not listed as a candidate, then of course the probability of winning is zero. You have to make sure that the probability of the certain event is 1. You have to make sure that the sum of the probabilities of these joint events, mutually exclusives, are 1. Like if you assign a probability of winning to Trump and then a probability to Clinton, and you don't consider any other possible outcome, just make sure that the sum of the two probabilities is 1. Probabilities are often expressed in percentage terms, which doesn't change anything. So instead of 0, 1, it's 0, 100%. And so this is the Bayesian definition. We were referring to events here, and let's still refer to events and define a probability distribution. What is a probability distribution? It's nothing else than an analytical function that describes probabilities. And usually it is a parametric function. So it includes parameters. And usually the probability distribution only depends on parameters and the event. Of course it depends on the event, because it must depend on the event. We define an event and then probability distribution gives the probability. But it may also depend on external, exogenous variables that we may want to consider. Especially for incorporating our knowledge on the human impact, our knowledge on sustainability, we may desire to include an external, exogenous variable. It's possible. For instance, some people include time in order to keep into account that probabilities are changing in time, may be changing in time. Usually they change in time when there is human impact, when there are other forcings that may change them. Given that the probability distribution depends, so one of the independent variables for this function, because the probability distribution is an analytical function, given that one independent variable is the event, usually we refer to random variables, because an analytical function should depend not really on an event, but on a variable. If it is an analytical function, it should depend on a variable. So usually we associate to event the random variables in order to make them tractable. And how can we estimate our probability distribution? Basically what we do is try to assess through Bayesian or frequency definition the probability of selected events, and then we try to interpolate this probability through an analytical function. And we will see some examples right now. So let me make an example which refers to, it's reported in my, sorry, I move a bit forward. It's reported in my lecture. This is a very interesting sample. It's very simple, and it's interesting because it's simple, which consists in estimating the probability of the result of tossing two dice. And you know that a die, two dice, and a die is may provide an outcome which is an integer between 1 and 6. And if the die is fair, you have a probability of 1/6, 1 divided by 6, for each of the outcomes. If you roll 2 of them and you compute the sum of the outcomes, you obtain an experiment which is formed by rolling twice a die and taking the sum. And the question is, what is the probability of this sum? First of all, the sum varies between 2 and 12. And in order to get these probabilities, you just have to make a very simple computation, and therefore let's make this computation in order to estimate the probabilities of individual outcomes in order to get something that we want subsequently to interpolate. Let's start from the very simple starting point of 2. And 2 means that you may have only one possible outcome that gives 2. Is 1 plus 1. There is no other choice. Like for 12, you have only possible outcome, 6 plus 6. And therefore, what is the probability? The probability is 1 over 6 times 1 over 6, because the probability of 2 events, 2 subsequent events, is obtained as the product of the probability of the individual event. So what is the probability of getting 1 is 1/6. What is the probability of getting 1 in the second roll is 1/6. You multiply them and you obtain the probability of getting 1 plus 1. And this is first basic law of probability. So what is then the probability of getting 3? You have 2 possibilities for getting 3. For getting 3, you may have 1 in the first attempt and 2 in the second, or you may have 2 in the first and 1 in the second. So you have the probability that is twice, the probability of getting 3 is twice the probability of getting 2. Twice, because you have 2 possible outcomes, while for the result of 2, the possible outcome is just 1. Okay, so what is the probability of getting 4? You may get 4 by 3 combinations, which are 1, 3, 3, 1, and 2, 2. And therefore, the total probability is 1 over 36 multiplied by 3. So 3 divided by 36, which means 1 over 12. And then you move forward, and the most likely number is 7. And so you see that you obtain by simply, you could obtain the same picture by making experiments, or you may obtain this picture, as I did, through a Bayesian estimation of probabilities, because I assume that the die is fair, and then I can easily compute individual probabilities. But then I can interpolate these outcomes with a function, like a triangular function, which gives an approximation. And if I make this interpolation, for instance, I can use a triangular function, or I can use a smoother function. If I make this interpolation, I obtain the probability distribution, or probability function. We use them as synonyms: probability distribution, probability function. You may see some textbooks which use probability distribution function. Of course, the question here is how I can perform this, how can I identify the best function to interpolate it? Just one side consideration. There is one thing that I said, that the probability of getting 2 is 1 over 36, and I gave you the rule for computing it. I said the product of the 2 individual events, and you may ask me, but can you please prove this? Can you provide a proof that indeed the probability of getting 1 is 1 over 6, the probability of getting a second one is again 1 over 6. Can you prove that the probability of getting the 2 is 1 over 6 times 1 over 6? So my reply is, if you look on Wikipedia, there is a demonstration somewhere, but it is much simpler as a technicians and engineers to perform experiments. So try to perform experiments. Take a die and start rolling, And it's just enough that you perform like 50 experiments and you see how many times you get 2. And of course, to get a good estimate, you need to make many experiments. If this probability is indeed 1/36, 50 trials may be too few in order to get even one outcome. Because in principle, for getting 2 outcomes of 2, you should perform in principle at least 72 trials. So if you perform 50, it may be that you don't get none of them. But keep in mind that probability, sometimes it's a complicated way, complicated because we need analytical expressions and proofs. It's a complicated way to express what is clear by intuition. And this is essential for you in order not to be concerned by probability. Probability is just the study of the frequency of events. There is nothing hidden there. There is nothing mysterious. Everything can be proved by making experiments. If you are just patient, then it's very simple. And then, of course, when you want to translate in mathematical terms, and we need this as translation because as engineers we need functions to make the problem tractable, of course it becomes a bit complicated. So if you look only at the final result, like the Gaussian distribution, oh gosh, it's very complicated. But if you look at the premises, and if you look at what it means with the eyes of an engineer, it's nothing else than intuition. So probability is just a set of tools for translating what we see, the frequency of what we see in mathematical terms. So it's just a set of tools to profit from experience. Okay, let me go back to the probability distribution, because there is one thing that is, I think it's one of the most complicated steps to understand probability. And I'm trying to make it simple. Because so far we referred to events implicitly that can be translated in random variables which are integer. So it was not by coincidence that I made the case of the river overtopping or not, because I wanted to refer to an integer random variable. Overtopping is 1, non-overtopping is 0. In this case it's a binary variable. Tossing a coin, another experiment that I mentioned, is represented by a binary random variable. Rolling a die, another example that I made, is based on the random variable is an integer variable varying from 1 to 6. So it's very simple to assign probability to each outcome because the related random variable is integer. Now let's refer to river flow. River flow is a real variable, a real random variable. Real means that there are infinite possible outcomes. It's not like the case of the die, where the outcomes are just 6. There are infinite possible outcomes. So what happens if you define probability according to the frequencies definition in this way? Simply, it occurs that the number of times that when performing the experiment you get a real number, a given real number is 0. Because a real number is a number with an infinite number of digits. So what is the likelihood of getting, when you look at the river flows, this precise real number with the infinite number of digits? It's 0. It's 0. Even if you consider the river flow with only 2 digits, like 3, 0.05 cubic meters per second. So you consider Q equals 3 times 3.05 cubic meters per second. And you look at an historical series. So what is the likelihood of getting this precise value in an historical series? Is 0. I mean, you may be lucky that you find one, but still, when you estimate the probability, it becomes 0. So this definition, this frequencies definition doesn't apply, and also the Bayesian definition doesn't help you to estimate the probability for a real number. So we need to make some modification, and this, as I said, it's the step that probably is more complicated to explain and to understand, but indeed it's very simple. What is an ideal solution is to refer to intervals. In fact, when we look at the river flow, we are not interested in knowing whether this number is likely. We are interested in knowing whether flow above a given threshold is likely, and the threshold may be given by the level of overtopping LEV, or we may be interested in knowing how much is likely to get a river flow within a certain interval. Like when I'm studying droughts, I am interested in getting the probability that the river flow is lower than a given value. So when I study peak flows, I'm interested in getting the probability that the river flow is higher than a given value. When I'm studying drought, I'm interested in getting the probability that the river flow is lower than a given value. And this means referring to intervals and not to precise values. So, let's now